Learn something new every day for everyone. Have something you want to learn? Submit yours at lumolab.org. Learn something new every day for everyone. Have something you want to learn? Submit yours at lumolab.org.
The fundamental question is this: why do neural networks generalize at all? In the worst case, with enough parameters, a network can memorize any training set perfectly and give terrible performance on new data. Hinton and Van Camp realized that generalization depends on an information bottleneck. The network must compress the training data into its weights, and then decompress those weights into predictions. For generalization to work, there must be much less information in the weights than there is in the training outputs. If the weights contain too much information, they've simply memorized the training cases. The minimum description length principle, developed by Jorma Rissanen, gives us a rigorous framework for this intuition. The best model is the one that minimizes the combined cost of two things, describing the model itself and describing the misfit between the model and the data. Think of it as a communication game between a sender and receiver. The sender sees both inputs and correct outputs, fits a neural network, then must communicate the weights to the receiver. For each training case, the sender also sends the discrepancy between the network output and the correct output. The receiver adds this discrepancy to the network output to reconstruct the exact target. The total description length is the sum of the bits needed for the weights plus the bits needed for the errors. To apply MDL, we need coding schemes for both the data misfits and the weights. If errors are real numbers, infinite information would be needed, so we quantize them finely with fixed width. The coding theorem tells us that if sender and receiver agree on a probability distribution assigning probability mass p to each possible quantized error, we can code the error using -log p bits. To minimize expected bits, the best distribution is the true one. For convenience, assume errors are drawn from a zero-mean Gaussian with standard deviation sigma. For output unit j, the data misfit cost becomes k times n plus half n times log of the mean squared error over n. Remarkably, minimizing description length under Gaussian assumptions is equivalent to minimizing the usual squared error. The Gaussian assumption provides the MDL justification for why we use squared error in the first place. Now for the weights themselves. We can code them the same way. Assume they're drawn from a zero-mean Gaussian with some variance. The description length of the weights is proportional to the sum of their squares, exactly L2 regularization, or weight decay. The total description length becomes the data misfit term plus the weight cost term. This is just standard weight decay, but now with a principled interpretation. The regularization parameter is not arbitrary. It reflects the trade-off between model complexity and data fit in bits. This connection explains why L2 regularization works. It's the optimal code for Gaussian-distributed weights. But Hinton and Van Camp went further. Standard weight decay is a fixed penalty. What if we allowed weights to be noisy? In the MDL framework, very noisy weights can be communicated very cheaply. Here's the setup. Sender and receiver agree on a Gaussian prior. The sender has a Gaussian posterior for each weight. The number of bits to communicate the posterior distribution is the KL divergence from prior to posterior. For Gaussians, this KL divergence has a closed form, log of sigma posterior over sigma prior plus sigma prior squared over sigma posterior squared minus 1 all over 2. This lets us compute exactly how much information each weight contains. The key insight: weights with high uncertainty, noisy weights, cost fewer bits to communicate. We can optimize the noise level during learning to find the sweet spot between fitting the data and keeping weights simple. There's an even deeper insight: the bits back argument. When the sender communicates the weights, the receiver doesn't need to receive all the bits explicitly. Some information can be inferred from the data itself. Here's how it works. Step 1. The sender collapses weights drawn from the posterior into a discrete code. Step 2. The receiver uses the data to infer some of the weight information, effectively getting bits back. The practical result? We only pay for the information in the weights that cannot be predicted from the data. This is the foundation of what we now call variational inference. The KL divergence term represents the actual information cost after accounting for bits back. This paper was decades ahead of its time. Published in 1993, it laid groundwork for modern Bayesian deep learning. The paper also provides practical methods for computing derivatives. For a network with nonlinear hidden units but linear output units, the exact derivatives of both the expected squared error and the information in the noisy weights can be computed efficiently, without time-consuming Monte Carlo simulations. The trick is to propagate the noise through the network analytically. For linear output units, the noise in the weights induces a Gaussian distribution over outputs, making the expectations tractable. This computational efficiency was crucial for making the method practical in 1993, when compute was orders of magnitude more expensive than today. Every concept in this paper appears in modern deep learning. The noisy weights idea became variational inference in Bayesian neural networks. The KL divergence term appears in the variational autoencoder loss function. The bits back argument is the foundation of information bottleneck theory. Modern weight quantization methods, from binary neural networks to 8-bit inference, are direct descendants of this work. The lottery ticket hypothesis, which finds sparse subnetworks that can be trained in isolation, is exploring the same space. How much information do weights really need? Even modern techniques like knowledge distillation can be viewed through this lens. The student network learns a compressed representation of the teacher's knowledge. The key insight from Hinton and Van Camp is that regularization equals limiting information in the model. Weight decay isn't just a magic trick to prevent overfitting. It's the optimal coding strategy for Gaussian weights. Noisy weights aren't a hack. They're a way to make weights cheaper to communicate. The amount of regularization isn't arbitrary. It reflects how many bits we're willing to spend on describing the model versus the data misfit. This perspective unifies many seemingly ad hoc techniques under one information theoretic framework. It also explains why simpler models generalize. They literally require fewer bits to describe, leaving less room for memorizing noise.
Thanks for watching, and keep learning. Thanks for watching, and keep learning.